Okay, we have this final relation which represent the work done in moving a system from position 1 to position 2 which is equal to this term, like this is the total force acting on this system, and this total force is basically a sum of two forces. One is this external force and the other one is internal forces. Now we consider this term first. Okay, this term first, like consider the left hand side of, I call this equation as equation A. So we can write it as like this: sum over I, integral from 1 to 2, the limits of the integral is from position 1 to position 2, fi dot dr, which is equal to, as we know that the force is equal to rate of change of momentum dp over dt. So the force on ith particle will be equal to the rate of change of momentum of ith particle. Now we know that momentum is P is equal to mass time velocity. So if it is the ith particle momentum, then this will be the mass of the ith particle and this will be the velocity of the ith particle. So we have this Fi, which is equal to d over dt of mi vi. But mass is constant, so we can keep it outside of this differential or this operator. So we have mi dvi over dt. So this total force on a ith particle can be replaced by this term now. So we have this one, which is sum over I, integral from 1 to 2. We have Fi, instead of Fi I will put this one, which is mi, and then we have dvi over dt dot dri. So these are all vectors, so we have to put the vector notations here. Now here I will apply the chain rule, and the rule is like we have this term which is equal to sum over I, we have integral from 1 to 2, we have mi. Now we have d, I will apply the chain rule here to this term. So we have dvi over dt, which can be written as dvi over dri into dri over dt. Okay, and then we have this dri. So this can be written as sum over I, integral from 1 to 2, we have this mi, and we have this dvi over dri, and we have this dri over dt, but this is the rate of change of displacement, which is basically velocity vi into dri. Now this dri cancel with this dri, so we left with sum over I. Now mi is constant, so I can keep it outside of this integral, so mi is here, and we have integral from 1 to 2, and we have dvi into vi, so I can write it as vi dvi. Now this can be written as like this. So on this side we have this term, which is in sum over I, integral from 1 to 2, we have fi dot dri, which is equal to, on this side we have this one, sum over I, we have mi, integral from 1 to 2, and we have vi dvi. So the integral of vi dvi is, I can write it here, vi dvi. Now this can be written like this: sum over I mi integral, sorry, not integral. Now I will apply the integral. So we have this one, which is vi square over 2. If I apply the integral to this vi dvi, we get vi square over 2, and then we have the limits of the integral is from 1 to 2. So here I can write this is equal to sum over I. Now I'll bring this mi inside. So we have this mi vi over 2, and the limits of the integral are from 1 to 2. So this can be written like this: sum over I. We have this term, which is mi vi over 2 at position 2 minus sum over I. We have mi vi over 2 at position 1. Now the terms here in the bracket, like this term here, like here we have this mi vi over 2. This represents the kinetic energy. Because we know that kinetic energy of ith particle represent the kinetic energy of ith particle. Now kinetic energy of ith particle is half mv square. This is basically the kinetic energy, which is half mv square. Sorry, this is v square. So here we have square, here we have also v square. So this is kinetic energy is equal to half mv square, but kinetic energy of ith particle will be equal to half mi vi square. So this term basically represents the kinetic energy of the ith particle. So if there is a summation, then this whole terms represent the kinetic energy of the whole system, because we have the summation now. So the summation means this is the kinetic energy, there is a sum. So this is the kinetic energy of first particle plus second particle plus third particle. If we add all the kinetic energies, we get the total kinetic energy of the whole system. Here we have this 2 and this 1. So this term here, this term represent, so the first term okay on the right hand side represent the kinetic energy of the system, not of the ith particle. Okay, it is the kinetic energy of the system at position 2, because we have two positions. Initially the system was here, which I represent by position 1 or configuration 1. We apply the force, we bring the system to this point, this position or this configuration, which is 2. So this term here represent the kinetic energy of the system at this point. It represents the kinetic energy of the system. This one represents the kinetic energy of the system at this point, and this represents the kinetic energy of the system at this point. So we can say that the first term represents the kinetic energy of the system at configuration 2. And the second term shows the kinetic energy of the system, not of a single particle. Okay, it's the kinetic energy of the system at configuration 2, at configuration 1, sorry. So overall I can write this is like this. So we have this term, on this side we have this part, which is sum over I integral from 1 to 2 fi dot dri. Okay, so I can write sum over I integral from 1 to 2, we have fi dot dri, which is equal to, this is the kinetic energy of the system at configuration 2, so I represent it by T2, where T represent the kinetic energy, and this is the kinetic energy at configuration 2 minus T this term, which is kinetic energy of the system, which I represent by T, and this is the kinetic energy of the system with configuration 1, so I represent it by T1. So this is the kinetic energy of the system at configuration 2, and this is the kinetic energy of the system at configuration 2, configuration 1, sorry. So this whole expression shows the difference in kinetic energy, because this is the difference in kinetic energy at two different configurations. Now I call this equation as equation B. So we have this equation A, okay. In this equation A, I solve this part, like the part on the right hand side, left hand side of this equality sign. I got this one. I call it equation B. Now next we will move to solve this term, which I encircle by this red line. So here I will keep it in order, so that now let's move to this term, okay. So for that I consider the first term on the right hand side. Consider the first term on the right hand side, which is sum over I integral from 1 to 2 Fi external dot dri. Now we know that, here I will explain the conservative force again. We know that a force is said to be conservative. A force is said to be conservative if the vector product of force, or del cross F, or the curl of force is equal to 0. This is the necessary condition for a force to be conservative. Like if you have asked to find whether the force is conservative or not, then you will operate this operator with a vector product with this force, and you have to see whether the vector product of this del operator with F, if it is equal to 0, then we can say that the force is conservative. If it is not equal to 0, then the force is non-conservative. Now I suppose that the force is conservative, so if the force is conservative, then it means that del cross F is equal to 0. And we also know that the curl of, we know that the curl of gradient of a scalar function, okay. Scalar function is always 0. What it means, if we have a scalar function, let's suppose the function is v, okay, this is the function. If we have this scalar function, then we have this rule that the curl of gradient of this scalar function is always equal to 0. This is the curl and this is the gradient. So the curl of gradient of scalar function is always equal to 0. This is the basic mathematical rule, calculus. Now this is, let's say, equation 1, and this is equation 2. If we compare equation 1 and 2, then we can write, this is the same situation, because we have this vector, here we have this curl of this vector, here this is the vector, and here this is represent the curl of this vector. So that means that if we compare both this equation, then we can get F is equal to minus del V. Now here the negative sign shows that the force direction is in the direction of decreasing V. Here the negative sign shows that the direction of force is in a direction of decreasing V, where V is the scalar function, or we call it the potential. Now this is, we already discussed it in the class more in a detailed way, so here I just I just explain it again and just to revise the old memories. Now if I suppose that if here we have this external force, okay, if this external force is conservative, then we can write this external force is equal to negative gradient of this potential. So the external force, because the force was conservative, we have these rules, and we also know that this is the basic condition. So from that we got this relation. Because why we got this relation? Because we suppose that the force is conservative. Now the external force we also consider it to be conservative. So if it is conservative, then from the external force we get a similar expression like this. If I external is equal to minus negative gradient of potential. This is the external force on ith particle, which is equal to the negative gradient of the potential of ith particle. So it means that this term now can be written like this: sum over I integral from 1 to 2 if I external dot dri, which can be written like this. We have sum over I integral from 1 to 2, and we have, instead of this external force here, okay, I will put minus del IVI, okay, and then we have DRI. Now this can be written like this. I use a separate, this can be written like this. I will bring this negative sign outside, so we have minus sum over I integral from 1 to 2, and we have del I VI dot dr. Now we know that del I VI, what it means. It is del I VI basically represent partial VI over partial RI. Now del V dot dr, this is equal to del V is basically partial V over partial X into I plus partial V over partial Y into J plus partial V over partial Z into K. This is from this del V. And we know the dot, we have DRI. DRI is DXI, DX into I plus DY into J plus DZ into K. So the dot product of these two vectors will give us partial V over partial X dx plus partial V over partial Y dy plus partial V over partial Z into dz. Now this is basically what? dV, where V is a function of x, y, and z. If V is a function of x, y, and z, then we can write dV is equal to partial V over partial x dx plus partial V over partial y dy plus partial V over partial z dz. Okay, so this whole term del V dot dr basically give us dV. So here we have this term, okay, del V dot dr, from this we will get dV. But here we have this subscript I, so I will use I here. So we have this term which is sum over I integral from 1 to 2. We have this Fi external dot dri, which is equal to sum over I with negative sign here. We have, now these terms I will replace it by dvi. with integral from 1 to 2. Now this can be written like this. Now this can be written like minus sum over I. Now this is basically Vi. If I integrate dVi, we get Vi, and the integral is from, limit of the integral is from 1 to 2. So we have this expression, which is, I'll keep minus sign outside. So we have sum over I, Vi, but Vi is at configuration 2, the upper limit is 2, and then we have minus sum over I, we have Vi, but Vi is at configuration 1 because upper limit minus lower limit. Now this can be written like this. I'll bring minus outside, inside. I can keep it like this. So here I have this term. I can write it like this. Minus, we have sum over I, Vi, and we have these 2, minus sum over I, Vi, and we have this 1. Now this term here, this term, Vi basically represent potential energy of ith particle. So it means that this, if there is a sum over I with Vi, will represent the potential energy of the system of particle. So it means that this term, here we have this sum over I, Vi 2, represent the potential energy of the system at configuration 2. Similarly, we have this term sum over I, Vi at 1, basically represent the potential energy of the system at configuration 1, and that potential energy I represent by V. So we have this whole expression here, we have this one, sum over I integral from 1 to 2 Fi external dot dri. So here on this side we have this thing. So we have this expression sum over I integral from 1 to 2. We have this Fi external dot dri, which is equal to, we have this negative sign, and this is the potential energy of the system at configuration 2, and this is the potential energy of the system at configuration 1. But this potential energy is due to external force, so I put external here and ext here. So this is the potential energy of the system due to external force at configuration 2, and this is the potential energy of the system due to external force at configuration 1. So I can write it like this, sum over I integral from 1 to 2. We have this Fi external dot dri. So we have this vector notations also. So remember these notations. Okay. So here we have also this notation. So this will be equal to, if I apply this negative sign here, then we have this V1 first minus V2 is later. So first we have this potential energy of the system at configuration 1 due to external force, and this is the potential energy of the system at configuration 2 due to external force. So this is my equation C now. So I solved this second term also here. So from this term I got this one, from this term I already got this one, equation B. So we have only the last term left here, which is this one. I encircle this last term by this one. So I will solve this last term in the next video. Thank you.